Well, a very happy Tuesday evening to you all. Thank you for coming aboard the General Ham Radio class. General class is the intermediate license for amateur radio in the United States, and we've been rolling along on a class to prepare us to take a 35-question multiple choice test, which is how you get your general upgrade license for those who already have a technician license. Morse code is no longer required, so if you're interested in ham radio, send me an email or just start watching the shows here and get in contact. We'll get you straightened around. Anyway, we're going to be talking tonight about Chapter 7 from this book. This is the General Class License Manual from the American Radio Relay League, the 10th edition. That's the book that you want because it's got the current questions and answers in the back. All of the questions and answers that might be on your test are there. We're going to cover them all in class as we go week by week, chapter by chapter in the book. And there's only 9 chapters in the book, so if we're on Chapter 7 tonight, well, let's take a look at the schedule, Bruce. So here we have, and Bruce, if you put it on auto instead of on just cut, transitions are a little less jarring, but here is the schedule. I can maybe do that from here. It was because I had to restart it. Well, I can't do it from here. We'll do it at the break. Anyway, this is the schedule for up and coming. Tonight is antennas. I'm Gary, by the way, your instructor, Whiskey 4 Echo Echo Yankee. Next week, Dave, KE4EA, will give us a presentation on propagation. And then the final week of chapters is Chapter 9, which is safety, electrical and RF safety, and a practice test. We'll take a practice test together here in class. 35 questions, see how we're doing. And then our very last class will be on April the 15th. We'll come back here and just take 2 practice tests together. So that's the plan. So tonight, antennas. And antennas are really the thing that even non-technical hams can build because they're not that complicated, but there are some principles that we need to understand. And so we're going to go ahead and do that. And we're going to start with section 7.0, which is not in your book. I made it up. And why is it not? Okay, there we are. It wasn't advancing. I don't know why that was. We're going to start with something, some basic principles, some definitions, some things for you to consider. So the first thing I'd like you to consider is the thing that we call skin effect. And so here we have at the very top is a large conductor of, let's say, copper wire. We're looking at a cross section of it. And at DC, or very low frequencies, like 60 hertz for power, whatnot, all of the copper in the conductor is being used to carry electrical current. But an interesting thing happens as you raise the frequency. All of a sudden, the current flows not in the center of the conductor, away from the center, and is very pronounced the higher radio frequencies that you go up into, and especially microwave, etc. But the radio frequency current only flows on the outer part of the wire. And the inner part of the wire isn't even used. It doesn't even have to be there, which is why sometimes you'll see wiring in big high-power transmitters consists of copper plumbing, because you don't need the center. You just need the outer surface there because of the skin effect. Now, why do I mention that to start us all off? Well, because the most common transmission line that hams use is coaxial cable. And this is a trick question, but you know the answer if you were in my technician class. But at radio frequencies, how many conductors are there in this coaxial cable? If anybody knows the answer, go ahead and unmute and let me know.
There are 3. 3?
Yes, there are 3 conductors. That's the right answer. You say, Gary, 3? I only see there's a center conductor here. And there's the braid, the shield. Where's the third? It has to do with the braid. The inside surface of the braid is one conductor that is working alongside the center conductor here, and that's where the energy from your transmitter or from your antenna is being conveyed between the center conductor and the inner part of the braid. But the outer part of the braid is actually an independent conductor because of skin effect. And many times we forget about that and we hook our coaxial cable to the center of a dipole antenna and wonder, why doesn't it work the way we thought it should work? Because we've forgotten about this invisible third conductor. So we're going to carry on, but we'll come back to this as we talk about dipole antennas. The basic reference antenna that physicists use is something called an isotropic radiator. It's a point source antenna. It's infinitely small and radiates infinitely well in all directions. We can't build an isotropic antenna, however, because of reflections and other things that go on, but it's a good engineering reference. And you'll hear of antennas that we do use being referenced to an isotropic radiator. Well, that's what they're talking about here, is a point source, a theoretical antenna. Okay, here's our dipole. And again, remember that it's a half wavelength at the frequency that we want to operate on. And the dipole antenna is our wires that go off to the left and right, for example. It's fed by a feed line, could be that coaxial cable. The antenna in total is a half of a wavelength long. So we call it a half wave dipole antenna. And this is probably the easiest and quickest antenna to assemble and to put up in the air and to get on the air. So keep that in mind. The length, how do we know what the length is? Well, if you're an American like we are, in the United States we use, feet and yards and whatnot. So if you want to measure the approximate length of a half wave dipole antenna, there are some factors, but 468 divided by the frequency in megahertz. And the factors that I was going to mention is that insulated wire, because it slows down radio frequency travel to just below the speed of light. Actually, those antennas can be shorter because they look electrically longer than they really are. But this is a good starting point, 468 divided by the frequency in megahertz. So if you're on our mailing list, you got an email from me before class, and I referenced this video. And if you haven't watched it yet, I encourage you to do so. It's about 90 minutes. It's part of the Ham Radio Now series from Gary Pierce, and it's called Standing Up for Standing Waves. And Bill, I can't think of his name now, is the presenter. And it's a really interesting look at a demonstration of radio frequency physics and antennas and transmission lines I think you'll find interesting. Two takeaways, though, from this presentation from the Standing Up for Standing Waves is a quarter wavelength of wire or transmission line is what we call an impedance inverter. If there's a low impedance at one end and there's a quarter of a wavelength away, then there'll be a high impedance at the other end. So a quarter wavelength of transmission line is an impedance inverter, whereas a half wavelength of wire or transmission line is an impedance repeater. So for a half wavelength long wire, if there's a low impedance at one end, there'll be a low impedance at the other. Keep those in mind. And impedance, what we're talking about here, rather than think about ohms, rather think about a ratio. Think about the ratio of voltage to current. So here's, voltage is the pressure pushing current through a conductor, and resistance is trying to impede that flow. So impedance is the ratio of voltage and current. And going back to our half-wave dipole antenna again, current and voltage are distributed along the antenna differently. At the center of the antenna, where we are going to connect our feed line, is the high current point of the antenna. This is where maximum current is, whereas the current tapers off as it goes toward the ends, and here is actually the maximum voltage point at this end and at this end. Well, let's put it in motion. If you look here at this animated GIF, the blue is the current, and the current is actually the place where radiation occurs from the antenna. So you always want to get the maximum current point as high up in the air as you possibly can. The ends of the antenna are where the voltage maximums are, and that's why we have high voltage insulators on the end of amateur radio antennas. They're not there for looks, but rather because there are high voltages that can exist there. And so implied in this, high current and low voltage here at the center means low impedance because of the ratio. Whereas we have at the ends high voltage, low current, this implies high voltage. And we use something called Ohm's law for AC circuits. This is not strictly true, but this is a shortcut that we can use. And so if we know that the impedance is the ratio of voltage to current, well, if the current is high, we know that the impedance will be low. If the voltage is high, then we know the impedance also will be high. And so with a resonant antenna, remember resonant antennas are one in which the inductive reactance and the capacitive reactance cancel each other out. That's why we cut it for that specific length to get that property. You're then left with two R's. The good R, which is radiation resistance, which is what makes the antenna radiate energy out into space, and bad R, which are losses because of corrosion or bad connections. You try to minimize the bad R and maximize the good R for the best operating with your antenna. And again, the lowest impedance point for a half-wave dipole antenna is at the center, and the nominal impedance is about 73 ohms, which is a relatively good match to 50 ohm coaxial cable. And if we assume a 1 amp of RF current flowing at the center, and we know it's 73 ohms, we can do the calculation, and we know that there's going to be 73 volts at the center as well. And so also, we know that that's the equivalent of about 73 watts of power being sent to the antenna. So just kind of keep that in your mind as a factor. Now, I hear from a lot of people that say, well, Gary, I want to use an end-fed half-wave. So an end-fed half-wave antenna is what we would call a voltage-fed antenna. The half-wave dipole we've looked at so far is a current-fed antenna, but this one is a voltage-fed antenna using a ball-on that could be up to 49 to 1. I've got 9 to 1 there, but it could be even much more than that, which will raise the impedance on the output terminal so that you're feeding with high voltage at the end of the antenna. Again, it's a half-wave length long. Ignore this. This is directly connected. Impedance at the end is very high. So this is why you need that transformer to go from your 50 ohm feed line up to a very high impedance that might match the antenna. An antenna that I like is a version of this that goes halfway. It's the off-center fed dipole antenna. So a dipole antenna, center fed, is a single band antenna. So here an antenna for 40 meters, let's say, would be good for 40 meters. It will not work well for 20 meters. It may work well for 15 meters, which is the third harmonic. But generally, half-wave dipole antennas are single band antennas. Off-center fed dipole antennas also use a transformer, 4 to 1 or 6 to 1, and it's fed 1/3, 2/3 is the standard. Here, and by feeding it there, the impedance point over various bands stays about the same, about 200 to 400 ohms. And so the off-center fed dipole can be used on multiple different bands, which is why I like this antenna. I have a 160 meter off-center fed dipole and an 80 meter off-center fed dipole here at my station, and I use them all the time and work very, very well. That 200 ohm feed point impedance at that 1/3 point, we know that the voltage is going to be higher than it was at the center, but the current's going to be less than it was at the center because of the ratio. The power involved is going to be the same, and the benefit is that we get multiple bands of operation, but you will have to use like a 4-to-1 balun to feed the antenna. And a SWR sweep of an off-center fed dipole shows you the various resonances. Here's SWR dip, next band SWR dip, another band SWR dip, and another band. So the off-center fed dipole has a lot going for it. Now, dipole radiation, whether it's end-fed or center-fed or off-center fed, is kind of like a donut shape. And if we're excluding any reflections here, so here's the antenna is going through the middle of the donut here. That's the line of the antenna, and energy radiates out in this pattern. Now, if we were going to look down on the antenna, you'd see we're looking here at the end of the donut, and it kind of looks like a figure 8. Broadside, this is the antenna, going left and right. So the radiation pattern of the antenna is broadside to the plane of the antenna. And this is what it looks like now. We've moved the antenna to a vertical orientation here, up down, so you can see, but the energy is radiating out from the dipole antenna. Antenna height affects angle of radiation. So the lower an antenna is, the higher the angle of radiation will be. If you can get the antenna up higher, then these lobes start coming apart and going down, and you get radiation at lower angles, which can go out to the ionosphere, be refracted down, and go further distances. Now, that off-center fed dipole antenna, the two that I have, are oriented this way as inverted V antennas. And you can do it also with half-wave dipoles. Support the center of a half-wave dipole, and then have the legs droop down. This is it's a very common way of using a dipole antenna, and one of these is pretty much an omnidirectional antenna. But remember, I said you wanted the current point to be as high as possible, and this is true to that. If we know that this is the low impedance point for a half-wave dipole antenna, it's up the highest. It's going to get the maximum radiation, so that's what you want to do. But the most important thing to consider, if you're putting up your antenna and you're going, why isn't it performing? Besides that third wire, we'll talk about that in a second, is that, okay, here is a dipole antenna and its height above ground. And here is its radiation resistance, the good R, and here is its height above ground in wavelengths. So here's a half a wavelength above ground, here's 1 wavelength above ground, here's 1.5 wavelengths above ground. This graph works for any frequency. It just depends what you want to put up. But notice, low to the ground, the impedance of the antenna starts at about 10 ohms. It works its way up, and then even goes up to about 100 ohms. And then as you go up higher in height, it starts coming back down again. And then it goes back up again. And then it goes back down again. Notice that we would say in math, regressing to a mean. The average of these measurements is where we get the 73 ohms from. But if your antenna is lower than a half of a wavelength, well, you're going to be on this part of the curve, and the 73 ohms, you may be down here, and it's not going to be 73 ohms. It's going to be 35 ohms. So keep that in mind, that antenna height above ground. Now, this is above perfect Earth. That's what this graph is all about. Imperfect Earth, which is where we live, you notice it doesn't go quite that far down, but anything below a half of a wavelength, antenna height is going to have a real significant impact on the impedance of that antenna. Antenna gain in decibels compared to a dipole antenna, or decibels compared to an isotropic antenna. And as we learned in the technician class, a dipole antenna has 2.15 dB more gain than an isotropic antenna. So if we were reading specifications for a whiz-bang antenna that has a rated gain of 8.15 dBi, Well, how is that going to compare to a dipole antenna? We subtract 2.15, and then we find that the dBd gain, same antenna, same gain, just expressed differently, is 6 dB. All right, so that was my introduction, section 7.0. Questions? No, there are no questions. But I just wanted to give you that information as a background. So now let's jump into section 7.1, dipoles and ground planes. So there are test questions here. So what if we took that half-wave dipole antenna that we looked at before and we stood it upright? Well, it would be 1/4 of a wavelength high. And what if we took that other the half wave and ran it out at 90 degrees? And instead of running it just once, we ran a bunch of different radials, is what they're called, out at 90 degrees. This is a vertical antenna, specifically a 1/4 wave vertical antenna. And because it's only half height or half the length, this is all on the ground, the impedance of a ground plane antenna is going to be half of a half-wave dipole. So we said the nominal impedance of a half-wave dipole was 73. Well, the nominal impedance of a 1/4 wave vertical antenna is going to be about 36 ohms. Also a good match, relatively good match to 50 ohm coaxial cable, which is one of the reasons why the military kind of standardized for transmission purposes to use 50 ohm cable. And ground-mounted verticals, as we just saw there, use a lot of radials. Broadcasters use a radial every 1 degree, so you got 360 radials. Amateurs have discovered that if you can get 38 radials on the ground, that you're within 1 dB of being, the perfect ground plane. And you can actually have antennas that have vertical elements of different lengths. So you have an antenna here for 20, an antenna for 15, an antenna for 10. In fact, this is exactly the concept of the DX Commander line of vertical antennas that you can buy. I have one out here and it works very well. I worked Australia this morning on it, on 40 meters. It has various lengths of vertical radiators here that all are fed by a common coax. And the radials themselves can be on the surface of the ground. I just lay mine on the surface. Or you can bury them maybe 1 inch under the ground. You don't want to go down any deeper than that. If you go deeper, then you lose the impact. The radials don't help you out. I liken radials to the end of a pool. Have you ever done a kick turn? If you've been in the swimming pool and you get to the end and you turn over and you kick away from the end of the pool, it's the end of the pool, you're providing the energy with your legs, but you have to have the end of the pool to kick off of. Well, a vertical antenna has to have these radials to kick off of, and then the energy can go out. If you don't include the radials, if you did like I did when I was a novice, and just drove an 8-foot ground rod in the ground and called it good, your antenna will not be very effective. So keep radials in mind. Something you do have to consider with a vertical antenna are something called ground reflection losses. A vertical antenna has more of these. Ground reflection losses could be considered bad R. It has to do with an imaging of the signal and interference coming from the ground. So just know about ground reflection losses. They deal with vertical antennas. And if you can get your vertical antenna up high, if you can actually maybe raise the point of the antenna where you're feeding it to maybe 10, 15 feet off the ground, maybe suspended in a tree, and you run the radials down at an angle, 30, 45 degrees like this. These are called sloping radials. Of course, if the radials are on the ground, you can't do that. But if you can get this feed point up high and have these elevated radials, we said that the normal impedance of a 1/4 wave vertical antenna is 36 ohms. This little trick right here will actually raise the impedance of the antenna to 50 ohms and make it a much better match to 50 ohm coaxial cable. So it's a way that you can actually reduce reflections coming from the antenna. And with elevated radials, I've used these in the past, you really only need about 4 radials. You don't need 38. I mean, more would be better, but you can you can get an effective antenna with just 4 elevated radials. Oh my, let's talk about loaded antennas. Well, not loaded like this. Here we have a standard half-wave dipole antenna. We've seen it all before. Now we're feeding it with 72 ohm coax. You can do that as well. Again, the length of the half-wave dipole is 468 divided by the frequency in megahertz. And we said that this makes the antenna a resonant antenna. And so here we have a series resonant circuit. And this could be a diagram, of an antenna. It's got a capacitance of some value, and it's got an inductance of some value, and it's got a radiation resistance, the good R. And in a resonant circuit, the reactance of the capacitance and the reactance of the inductance are equal, and they'll actually cancel each other out. And when this happens, you're left with just the radiation resistance. So here is the formula for a resonant circuit. And in the general class, we don't need to go through and calculate anything. We do in the extra class. But I just want to put it up here to note that with a frequency of resonance, that's what this is going to be, if we increase the inductance, or if we increase the capacitance because of 1 over, any increase here will lower the frequency of resonance. So anytime we can increase L, we'll get a lower value of resonant frequency, or anytime we can increase C, we'll get, again, a lower frequency of resonance. Well, what is this all about? Well, loaded antennas. So a loaded antenna is one. Here's a vertical antenna. Here's the radials on the ground. We're feeding them this independently. And we have a coil. We're increasing the L. A coil is added into the antenna. And a capacitance top hat is added to the top. And so both of these things go to reducing the physical height of this antenna. It doesn't have to be a full quarter wave high anymore. Rather, with this loading, we can actually make them shorter, much shorter. That's how we get HF mobile antennas for cars, by using loading with L and C. By adding L and C, it's the same as making the antenna physically longer. We're making it electrically longer. But you pay a price, reduced operating bandwidth. And what are we talking about? Well, SWR, we want it to be below 2 to 1. Well, on a full-size antenna, you have a very broad range of frequencies, where here's the 2 to 1 point. Any of these frequencies, the SWR is much below 2 to 1. Your transmitter is going to be happy. You're going to radiate your 100 watts and everything. But with a loaded antenna, look at this. Only at like 1 frequency is it going to be really good, and then at the other frequencies, not. Which is why with mobile antennas, in many cases, you have to retune them. That's where the screwdriver antennas came along, using motors from old electric screwdrivers to drive the coil assembly and actually change the inductance as you're motoring along to match the frequency of your transceiver. So that's where screwdriver antennas came from. They changed their electrical length by turning the coil inside of a form, which is part of the antenna. Now, not to be confused, this is adding L to the antenna, but corona balls, these little things up here, it's to prevent you from poking your eye out, yeah? Well, no, the purpose is to reduce high voltage discharge at the tip. Remember I said at the end of the antenna you're going to have a high voltage point, and so to reduce arcing and sparking out here, they add this corona ball. That's what that's all about. You'll poke your eye out. No, you won't. All right, let's answer some questions. So what is the purpose of a capacitance hat on a mobile antenna?
Charlie?
Charlie is correct. To electrically lengthen what is otherwise a physically short antenna. It makes it resonant on a high HF frequency. And what is the purpose of a corona ball on an HF mobile antenna?
Don't poke your eye.
It is. Yeah, you don't poke your eye, and to reduce RF voltage discharge from the tip of the antenna while transmitting. And what is one disadvantage of using a shortened mobile antenna as opposed to a full-size antenna?
Charlie.
Yeah, your operating bandwidth, the SWR bandwidth, may be very limited. And which of the following is a common way to adjust the feed point impedance of an elevated quarter wave ground plane vertical antenna to be approximately 50 ohms? Yeah, if you slope the radials downward. I've done this for an 80 meter and a 40 meter antenna, worked well. So which of the following best describes the radiation pattern of a quarter... Oops, somebody's blowing their nose right in our microphone. Okay. Which of the following best describes the radiation pattern of a quarter wave ground plane vertical antenna? What is the radiation pattern?
Delta.
Yeah, omnidirectional. And what is the radiation pattern of a dipole antenna in free space in a plane containing the conductor?
Alpha.
I heard alpha. Do we agree?
Bravo.
Yeah. Not Bravo.
No.
No, it is alpha.
Alpha?
It's a figure-8 pattern, and it's at right angles to the antenna. There's very little radiation off the ends of the antenna, so this one wouldn't work. And how does antenna height affect the azimuthal radiation pattern of a horizontal dipole HF antenna at elevation angles higher than about 45 degrees? That's a lot of words. I heard Charlie.
Delta.
I heard Delta. What do we think?
Charlie.
It's Charlie. When the antenna is less than a half wavelength high, the horizontal radiation goes almost vertical, and so the total pattern of the antenna is pretty much omnidirectional. It fills in at the ends, actually. So where should the radial wires of a ground-mounted vertical antenna system be placed?
Charlie.
On the surface or buried just a few inches below the ground? Mine are right on the surface. And how does the feed point impedance of a horizontal half-wave dipole antenna change as the antenna height is reduced to 1/10 wavelength above ground?
Alpha.
Alpha is what I think.
The feed point impedance. Bravo. It's going to at height it's going to be 73 ohms. Below a half wavelength, it's going to kind of go up and then down. But as you go down to a 1/10 of a wavelength, it's always going to be going down to that low of 10 ohms. So it steadily decreases. Of course, that was over perfect ground, but okay. So how does the feed point impedance of a half-wave dipole change as the feed point is moved from the center toward the ends? Feed point impedance. I heard alpha.
Alpha.
Yeah, it steadily increases. It's the lowest impedance point at the center, and as you move up toward the end, that's the highest impedance point. Ratio of voltage to current. And which of the following is an advantage of using a horizontally polarized as compared to a vertically polarized HF antenna?
Alpha.
I heard alpha. Remember, I talked about vertical antennas have that ground loss. Horizontal antennas do not have any ground losses, so that's an advantage. And what is the approximate length for a half-wave dipole antenna cut for 14.25 megahertz? Remember the formula? 468 divided by the frequency in megahertz. 468 divided by 14.25 is going to give us delta, 33 feet. And what is the approximate length for a half-wave dipole antenna cut for 3.550 megahertz? Again, it's 468 divided by 3.55.
So,
Charlie.
Yes, 132 feet. Very good.
so the book it says 492.
Yeah, I think that's.
I asked that in the chat.
Yeah, it's. I didn't see it. Sorry, but yeah, at 468. That's the one you want to use. So, what is the approximate length for a quarter wave monopole antenna cut for 28.5 megahertz?
Alpha?
Yes, that's
Alpha.
8 feet indeed. So notice how the antennas get shorter the higher the frequency is. So how does antenna gain in dBi compare to gain stated in dBd for the same antenna?
Oh, that would be Bravo.
Yes,
Bravo.
gain expressed in dBi is going to be 2.15 dB higher than dBd. And which of the following antenna types will be most effective as a near vertical incident skywave antenna for short skip communications on 40 meters during the day? I didn't specifically mention NVIS antennas, but they shoot their energy up to the sky, pretty much. And because I didn't cover it, my fault, I'm going to give you the answer. It's a horizontal dipole down low, placed between 1/10 and 1/4 of a wavelength above ground. Remember, it's going to have that omnidirectional pattern, and most of the energy is going to be shooting upwards, bouncing off of the ionosphere and coming down maybe on the other side of a mountain range that's nearby. So that's a NVIS antenna. So what is the feed point impedance of an end-fed half-wave antenna? End-fed half-wave antenna.
Delta.
Delta. I heard it that time. Okay, good. Yes, very high. Absolutely correct. It's going to be, we don't know exactly what it's going to be, but it'll be very high at that point. And how does a screwdriver mobile antenna adjust its feed point impedance? I heard it in there. You're doing good. Bravo. By varying the base loading inductance, that motor is adjusting a coil that is going up and down. That's an inductance, an L. So yes. And what is the common name of a dipole with a single central support? Alpha, inverted V antenna. All right. Moving on to Yagi antennas. These are directional gain antennas. And the driven element of a Yagi antenna is typically our friend, the half-wave dipole antenna. All right. Yeah, we didn't learn it for nothing. And something to know about dipole antennas and then elements on Yagis is that the larger diameter the element is, the greater the SWR bandwidth will be. So you can actually put up, these are called cage dipole antennas, which, remember, because of skin effect and other factors, this makes this look like it's a huge honking conductor, with a really large diameter, when it's a series of wires run to hoops and on. So it makes it look like a very big virtual conductor. Greater diameter for your element gives you a greater SWR bandwidth, which is also the reason why some antennas cost more than other antennas. So Bruce, if you get rid of me there for a second, on the left there is the old high gain TH3 Junior, which at the time when I made the slide was $539 at DX Engineering. Very small, very lightweight aluminum. 3 bands, 20 meters, 15 meters, and 10 meters. Over here on the other side is a Mosley CL33, $1,000. Okay, this is a higher power antenna, number one, but it's a trapped Yagi, and the elements are much, much thicker in diameter. So that's another reason why antennas don't cost the same, because they're constructed differently, and the SWR bandwidth is going to be much better with a larger diameter element. Now this is drastic. That's our mobile antenna, but I did that for illustration. So a famous axiom about vertical antennas, no matter the brand or the type that you do, they will receive and transmit equally poorly in all directions. It's true. You don't have any gain from a single element vertical antenna. So if you have an antenna, though, that has gain, you can direct the energy from the radio frequency energy from that antenna. Well, then it gives you a problem, though. You got to know which way to point the antenna. And the solution comes in the form of these. They're called azimuthal projection maps. And it's a map centered on one location, your location, and then it shows the bearings to others from that location, so that we can see here, centered on the United States. So if we're looking toward, I guess it would be Siberia out there, and out, so it's straight north. Europe at about 33 degrees to 40 degrees. Africa at about 90 degrees. South America, okay? So this gives you the bearing, the azimuthal bearing, well, Gary, I live in Podunk, wherever. How am I going to get a chart for my location? Hams, we're very generous. Go to the website of NS6T. And there you can go to this URL, and they will generate a map for free based on your location. You have to give them your latitude and longitude. And it's really handy, and so I recommend it. And if you can make a donation to them, that'd be great. Sometimes with directional antennas, we said, you can direct your energy in a certain way. Well, here's an antenna that has a cardioid pattern. It's heart-shaped, only the heart is upside down, okay? And so it's directing its energy over in this direction. So it's going to hear and transmit best in this direction from this point. But notice practically nothing, if not nothing, in this direction. There's a null right there. Well, a directional antenna can be used to null a noise source. So if you've got an antenna with a pattern like this, and you've got a source of local noise, if you point it away from the local noise, this can be very effective. So that's, sometimes it's not what you hear, it's what you don't hear that can make the difference in making a contact. All right, the Yagi antenna, named after the Japanese scientist Mr. Yagi and his partner Mr. Uda. We have the half wavelength driven element here at the center, and we have behind it a certain distance. In this case, they say 0.15 of a wavelength. It's about 5% longer than the driven element. The driven element is a half wavelength. Here is 1.05 times a half wavelength. And a director is shorter by about 5%. So we have a reflector, the driven element, this is where your coax is going to connect to, and the director. And so this is a 3-element Yagi beam. And you can also then have multiple elements, 5-element in this case, with our driven here, the half-wave element, a single reflector in this case, and then narrowing length directors. This will give you increased gain, but with a narrower bandwidth. Get in the camera here. Your beam width from the antenna is going to narrow the more of these director elements, for example, that you put on it. So it's very important then that you point it in the direction that you want to be transmitting in. And one of the measurements you can make with a Yagi antenna, here's one with a very narrow beam width, is what we call front to back ratio. It's the ratio of signal strength in the forward direction to signal strength in the reverse direction. That's front to back ratio. And it's one of the characteristics that are measured and calculated when you use antenna modeling software. And EasyNet used to be the amateur radio standard for years, but a lot of people didn't use it because it was expensive. $100 was the starting price, and then it went up. Well, he retired, Roy Llewellyn, and so he made it free for everyone. So you can go to easynet.com. I think still version 7 is the latest one, and you can download it. Now, there is a steep learning curve for this piece of software, and for another, which is called Monogal, which was developed by some Japanese and German hams. And this also is free antenna modeling software. And you can use either of these and put in the definitions of the elements of your antenna, and you can then calculate the physical length of the boom, the number of elements on the boom, the spacing of each element along the boom, and you can run projections as to the impedance, the beam width, the front to back ratio, and you can model it on the computer. So here again is our 3-element Yagi antenna. Now, with the 3 elements, remember we said that the dipole antenna, if we fed it at the center, is going to have an impedance of about 73 ohms. Well, when we add the reflector to the boom and we add the director, these are what they call parasitic elements. They're not connected to the coax, but they're in the near field of the dipole, and like parasites, they will absorb and redirect energy coming from the dipole. Again, absorb and redirect. And what happens there, since they're taking energy from the dipole, it's actually reducing the impedance of the antenna, of the feed point, from 73 ohms down to maybe 20 ohms. And so we have to compensate for that. And many times what they'll use is something called a gamma match, which is where you have your coaxial cable connected to the half-wave dipole-driven element. And with a gamma match, you can connect the shield directly to the center, and then using a capacitor-inductor arrangement, you can compensate and bring the impedance from 20 ohms back to 50 ohms to match the coax. Here's another view of a gamma match. Note that with the gamma match, the driven element can be connected directly to the boom. You don't have to have an insulator. Now, some antenna manufacturers didn't go this route. They didn't use a gamma match. Rather, they would insulate the 2 quarter wavelength sections of the half-wave driven element, well, like this. This is plastic insulation here. They've insulated the elements, and they use a stub matching technique, also known as a hairpin match, because it kind of looks like a hairpin. And at DC, this looks like a direct short, of course. You put an ohm meter across there, and it's going to read 0 ohms. But at RF, because of the magic of radio frequencies, it doesn't look like a short. It looks like an inductance. And the elements are made purposely shorter than normal by a certain amount. That makes the elements capacitive, and this added inductance then tunes that out. So hairpin match can also be called stub tuning. This is another way where you can add a section of transmission line in place of the hairpin at the center point. And BALAN is a short abbreviation for balanced to unbalanced. Whoops, what happened there? Okay. I lost my display for a second. Okay, let me go back. Balance is balanced to unbalanced, and I lost my laser pointer. Look at that. There we go. Here is our 50 ohm coaxial cable, and here we can take it to a balanced feed for feeding one side and then feeding the other side, and this disconnects that third conductor, the outer part of the shield. That's why we use balance. is to disconnect that phantom wire, that third wire, the outside of the shield, so that it doesn't impact tuning. Because otherwise, if it's directly connected to one of the elements, it's going to be an element on its own. And you don't know how it's going to tune out. So that's why we use balance, is to break that. We mentioned that some of the antennas we were looking at, like the high gain TH3 Junior or the Mosley, use traps. They're bandpass filters essentially, and it allows you to have an antenna that will be resonant on 10 meters using just the center part here, then on 50 meters going out one, and then 20 meters going out all the full length because of these filters on the ends of the elements of the antennas. They're called antenna traps, and it allows for multiband operation. All right, here's some questions. Which of the following describes an azimuthal projection map?
Bravo.
Yep, it's a map that shows true bearings and distances from a specific location. Which of the following would increase the bandwidth of a Yagi antenna?
Alpha.
You want larger diameter elements, it'll give you greater SWR bandwidth. And what is the approximate length of the driven element of a Yagi antenna?
Bravo.
Our old friend, the half wavelength dipole. And how do the lengths of a 3-element Yagi reflector and director compare to that of the driven element?
Alpha.
Yep, the reflector is longer by about 5%, and the director is shorter by about 5%. And what is the primary effect of increasing boom length and adding directors to a Yagi antenna? I don't think I really...
Alpha.
I didn't say it's alpha, it's the gain increases.
alpha.
It's one of those factors that you can figure out using the computer modeling software. And what does front to back ratio mean in reference to a Yagi antenna?
Charlie.
Yes, the power radiated in the forward or major lobe direction compared to that in the opposite. And what is meant by the main lobe of a directive antenna?
Delta.
Yeah, the direction of maximum radiated field strength from the antenna. And which of the following can be adjusted to optimize forward gain, front to back ratio, or SWR bandwidth of an antenna? Think about it. Read carefully.
Delta.
Delta.
You know my trick. Yeah, the physical length of the boom, that's one. The number of elements and the spacing of each element, all of those choices. So what is a beta or hairpin match?
Alpha.
It's a shorted transmission line stub, or that U-shaped to hairpin placed at the feed point of a Yagi antenna to provide impedance matching. And which of the following is a characteristic of using a gamma match with a Yagi antenna?
Alpha.
Yeah, it does not require the driven element to be insulated from the boom. Ladies and gentlemen, you've done great. You deserve a 5-minute break. So let's go take 5 minutes, move around, get something to drink, come on back, and we'll finish out the last sections in antennas.
cut us off.
Yeah, we're gonna cut you off.
Okay.
And we're back. We had a nice little discussion going on there during the break and talking about satellites. There are no amateur radio geostationary satellites in our hemisphere. One was talking about they were going to put one up. They actually did put one up over the equator over Europe and Africa. It's part of a Qatari satellite. So that's available in Europe, and they can use it. So you can probably sell your big antennas to hams over in Europe. They'd like it. 10 gigahertz is one of the bands they're using. Also, I had a question about, I've got my old TV antenna, the Channel Master. Can I use it as a Yagi? Well, it's a Yagi or a log periodic antenna. It's a directional antenna. It's a directional gain antenna for VHF, UHF. For those bands that TV was operating on. Also, if it's horizontally polarized, you could use it maybe for weak signal work, but you have to transform it. Also, it was never designed for transmitting. So, might have some problems there, but anyway. All right, let's carry on with section 7.3, loop antennas, which is apropos, because I'm going to be putting up one of these on Thursday. Bruce is going to come over and help me because I wanted to put it up in anticipation of a contest coming up this weekend. I'll tell you more about that. A full wave loop antenna is, in this case, we've got a quarter wavelength on each of the legs here. So here's a quarter wavelength, here's a quarter wavelength, here's a quarter wavelength, here's a quarter wavelength. And so this entire loop is one full wavelength. Length is about 272 feet, thereabouts. 267 is what I've been looking at. For 80 meters, or one for 40 meters, 142. You can feed it with the coaxial cable and a impedance matching transformer up here, or you can feed it with open wire line. So this is a horizontal loop antenna, and I'll let you know how it works out in the contest. Another version of this is one that N4KC has talked about, a Skywire loop. Bruce and I got a chance to meet Don Keith at the Huntsville Ham Fest last time around, and so he uses a 475-foot long loop, much longer. It's a non-resonant antenna. It's not designed for any particular band, but it is omnidirectional, has very low angles of radiation, but it does require an antenna tuner. So loop antennas, horizontal loop antennas, can be an effective antenna. Now, another kind of form of loop antenna was invented in Quito, Ecuador, by Clarence Moore, who was a missionary broadcast engineer at radio station HCJB in Quito. Religious broadcasters, still on the air today. And they were using Yagi beam antennas, but at the high altitudes up in Quito, the ends, because of the high voltage corona up there, the ends of the antennas kept melting off because of that coronal discharge. So he prayed about it. Literally, this is how he describes. He prayed, and he came up with this design with full wave loops. One for a driven element, which is one wavelength long, and the reflector element, which is 5% longer than the driven element. And lo and behold, the cubical quad was born. There are no high voltage points to melt off, and so they began using cubical quads at HCJB in Quito, Ecuador. So again, full wavelength loop for the driven element, reflector 5% longer. You can actually have directors 5% shorter. They're really big and kind of ungainly antennas, so maintenance can be difficult, but a 2-element cubical quad has the same amount of gain as a 3-element Yagi. Its radiation resistance is higher than a Yagi, so you can actually match it just with coaxial, 50 ohm coaxial cable. You don't need a gamma match or hairpin or anything like that. It works really well down low. I had a ham friend up in Michigan that used one down low. It's a shorter boom length than a Yagi. and they can be internally stackable. So you can have different lengths for different bands and feed them with a single coax. So cubical quad antennas. And cubical quad feed point and polarization, you can actually change the polarization whether you feed it at the bottom or if you feed it at the side. Top or the bottom, it becomes a horizontally polarized antenna. Either side, it becomes a vertically polarized antenna. And as I mentioned, you can have them nested inside of each other. Here's a spider quad, and you could feed it with a single coaxial cable, so it can be a multi-band directional cubical quad antenna. So this is using 4 sides. 3-sided antennas are called delta loops, and delta loops can be fed from the side or from the top or the bottom, depending on which way you have it up. So a 2-element delta loop again has the same gain as a 3-element Yagi. The driven element is a full wavelength, with each leg being 1/3 of a wavelength, and you've heard this before, the reflector is 5% longer than the driven element. If you go to a Hamfest, you may find one of these for sale. This is called a halo antenna, and it's a horizontally polarized but omnidirectional antenna. Looks like a halo, fed with 50 ohm coaxial cable. So this is a great antenna for VHF contesting, for example, where you can be listening on the halo antenna, you can hear a weak signal, and then try to ascertain where they might be by listening to a Maidenhead coordinator that they might transmit, and then you can point your directional antenna toward them to make the contact. So halos are good for omnidirectional use. I've got one of these sitting outside. I got a bunch of stuff. This is a receive loop, a loop antenna that's designed just for reception. It's bidirectional in the plane of the antenna. So directional in this way and directional over here. And those are receive loop active antennas, not to be confused with magnetic loops or transmit loop antennas. These can be used if you have limited space, for example, or you're in an apartment and you've only got a little patio outside, or even a balcony or whatnot. You might be able to use a magnetic loop antenna. You can build them yourself, or you can buy them. Here's one from Italy, the Ciro Mazzoni. Now this is their baby loop, believe it or not. It has a variable capacitor up here, a mechanical capacitor that you can adjust for tuning. The bandwidth on this antenna is very narrow, so you have to tune it all the time. So that's why it has a controller that senses the frequency of your radio to keep pace with the tuning. And again, that's a pretty hefty price tag, but if that's all you can do, well, go for it. Here's some questions. In which direction is the maximum radiation from a VHF-UHF halo antenna?
Charlie.
Halo antennas are omnidirectional in the plane of the halo. And in which direction or directions does an electrically small loop have nulls in its radiation pattern?
Bravo.
So if it has gain in the plane of the antenna, it's going to have nulls broadside to the loop. Very good. All right. Section 7.4, some specialized antennas. Back in the day, if we were doing shortwave listening, just an end-fed wire was usually the antenna that we used. Dave, if you'd mute them all, please. So an end-fed wire can be used with an antenna tuner as a transmit antenna. You're working the antenna itself against your station ground. The problem is that this is a high voltage point when you do that, and it's prone to having high voltage RF in the shack, and you may get a shock. Bonding the equipment and connecting it to the ground can help, but just now if you have the balun out here so that the high voltage point is out here, you're okay. but just to directly end feed a wire, you're going to have an issue because of the high RF voltages when you bring that into the shack. If you have a Yagi, well, even better is to have 2 Yagis. Stacking 2 identical Yagis results in a 3 dB gain versus a single antenna. So here we have a vertical mast, and here we have some horizontally stacked Yagi antennas. And what it's going to do is narrow the beam width on an azimuthal basis. You can also vertically stack antennas, one over the other. What this will do is to reduce the vertical beam width. It'll narrow that. Again, with 2 identical antennas, you're going to get a 3 dB increase. But the thing is that, okay, that's theoretical. By lowering your angle of radiation, because you're reducing the vertical beam width, then you can actually go out further, and for a distant signal, you might get an increase in signal strength much greater than 3 dB. I've got some stacked 6-meter Yagis that I can get 8 to 9 dB increase on a beacon station that we have nearby. And my friend Bob, ND7J, he put these 2 3-element 6-meter Yagis up on a mast. And got the mast already there, and there they are flying in the air. And he too reported signal strength well above the 3 dB theoretical gain that you get by putting 2 antennas together. Now then, if you get into Earth, Moon, Earth, well, my friend Matt, NU4E, has one of these. It's a Yagi 4-stack. With 6 dB of gain versus a single antenna, and this stack is reducing both the vertical and horizontal beam width because of the use of the 4 antennas. Oh, here's NVIS. That question was out of order. Near vertical incident sky wave is when we're sending from a transmitter up to the sky and having it bounce back down to stations here that might be otherwise separated because of these mountains. The military uses NVIS communications for technical squads out in the field. NVIS antenna is also known as a cloud warmer. Nearly any dipole lower than 1/4 of a wavelength high has NVIS properties. So, and you can even increase it by putting a reflector, which is 5% longer. All right, we know how that goes. And we talked about Yagis having traps, and all of a sudden, my computer says, no, I'm not going to move ahead. There we go. You can also put traps on dipole antennas. So here are the traps. And turning the single band antenna into a multi-band antenna. So if you can only put up 1 antenna because of, your yard or whatever else, this might be an option. The thing is, with multi-band antennas, including my off-center fed dipoles, there's poor harmonic rejection. So if you have a homebrew transmitter that puts out signals on 40 meters, but its second harmonic is on the 20-meter band and it puts out a lot on 20 meters, the antenna won't help you reject the harmonic radiation. So just keep that in mind, that multi-band antennas have poor harmonic rejection. Another multi-band antenna is a log periodic antenna. It has a continuous operation over a wide range of frequencies. It's different than a trapped antenna, which is band by band, but this is actually continuous in those frequencies. So it has a very wide bandwidth. You can have them rotatable or fixed. It does not suppress harmonics because it's a multi-band antenna. For the same size, it has lower gain than a Yagi, and you can see it is kind of mechanically complex. Now, fixed log periodic antennas might look like this, something tactically deployed out in the field, but I like this picture because you can see the relationship between the length of the antenna elements and their separation, and they vary logarithmically. You can kind of see the arc coming in here. So that's a log periodic antenna. Transmitting is only half the battle. Receiving is the other half. And if you can hear better, it can help you make the contact. And one of the best antennas for receiving is the Beveridge antenna, invented by Harold Beveridge of AT&T. It's a horizontal wire from 1/2 to several wavelengths long. It's used for receiving only, as it is said to have negative gain. But one thing its big benefit is it's immune to noise. So this is a pictorial of a common Beveridge antenna. Again, it uses impedance matching Balun transformer here. A length of wire, the longer the better, going into a 400 ohm, 450 ohm, they say here, non-inductive resistor to ground rod and ground radials. And so here's your basic Beveridge antenna. And Beveridge antennas are what they call traveling wave antennas. The radio wave comes in where the direction where the resistor is, and it builds up a signal along the surface of the wire, and that build-up voltage is then transformed and sent to your receiver. Beveridge antennas pointed in the direction that you want to be received from, especially on 160 meters, 80 meters, and 40 meters, can be really instrumental in hearing things that your transmit antenna can't hear. Beveridge antennas. All right, some more questions. What is a characteristic of a random wire HF antenna connected directly to the transmitter?
Bravo.
Yeah, I don't like the answer because I talked about high voltages, but station equipment may carry significant RF current. You're going to get shocked because of that. And in free space, how does the gain of two 3-element horizontally polarized Yagi antennas spaced vertically a half wavelength apart typically compare to the gain of a single 3-element Yagi? What's the theoretical improvement?
Charlie?
Bravo.
Bravo. 3 dB. Twice. 2 antennas, that makes sense. Twice. That's the theoretical. And what is the primary function of antenna traps? To catch antennas, of course.
Alpha.
Yeah, to enable multi-band operation. The traps are bandpass filters. And what is an advantage of vertically stacking horizontally polarized Yagi antennas?
Delta.
Delta, it narrows the main lobe in elevation. And which of the following is an advantage of a log periodic antenna?
Bravo.
Not Bravo.
Charlie.
Alpha.
It is alpha. It is wide bandwidth, wide continuous bandwidth. And which of the following describes a log periodic antenna?
Alpha.
Yes, element length and spacing vary logarithmically along the boom or the center spine of the antenna. And what is the primary use of a Beveridge antenna?
Alpha.
They're receive antennas only. You can't transmit on them, and it's for the medium frequency and low HF bands, 160, 80, and 40. And which of the following is a disadvantage of multiband antennas in general?
Delta.
Delta, yeah, they have no delta, they have poor harmonic suppression. All right, section 7.5, feed lines. We talk about feed lines and everything having a nominal impedance, and what we want is to have impedances matched. The source impedance of the transmitter matched to the characteristic impedance of the transmission line, matched to the load of the antenna. And when things are matched, we have a complete transfer of power. Here's our energy going from left to right, and it's all being radiated out into space. That's what we want. So if we look at radio energy as waves, I want you to think about waves of the ocean. And as they come up against the cliffs here, for example, they're going to rebound off of the cliffs. It may not be markedly noticeable, but that's what happens. That's a rebound wave. It's when energy hits a discontinuity. And so here's a rebound wave, an open circuit. If there's no load on the end, all of the energy that's being sent will be rebounded back to the source. The source could be our transmitter. It could be going along a transmission line, and we have an open circuit at the opposite end, and all of the energy will come back as a reflected wave. What we're likely going to be seeing, though, is something like this, a partial reflection, where the energy goes out to our antenna. Much of it is being radiated by the antenna, but some of it is being sent back as a reflected wave. Notice the polarity changed. That has to do with the impedances of the load. With a high impedance to a low impedance, you'll see that reversal of polarity. With low impedance to high impedance, it stays the same polarity. And the absolute worst case of total mismatch is hitting an open circuit, which is on the top, or hitting a short circuit on the bottom. Notice the polarity of the reflected wave changes because of the short circuit. When we have these reflected waves and we have the incident wave going out toward the load, the combination of those two makes standing waves. So if we look at the blue energy going from left to right, going from transmitter to the load, and look at the red energy coming back from the load going back to the transmitter, and where they peak together and they add together, you get the black wave. Notice the black wave isn't traveling from left to right or right to left. It's standing on the transmission line. That's why we call it a standing wave. If you have no reflected power coming from the antenna, then you will have no standing wave. But if you have reflected power, and the larger the reflected power, the higher the standing wave. And we're looking for a 1-to-1 standing wave ratio. That's a perfect impedance match. If you have that, then you're going to be doing fine. Here's a 1.14 to 1. That's near on perfect. Something new that I found from, I believe it was a student, they sent me a link here to the AT&T archives. And here is a mechanical representation in this YouTube video of transmission lines, standing waves, and reflected power. So if you got the time, take a look at it. It's kind of neat. So what can we do? Well, what most hams will do is try to get their antennas as closely matched as possible. And then after they do that, then they'll utilize something called an antenna tuner, also known as an antenna coupler. And what the antenna coupler does is, so here we have a transmitter that's coming into the antenna coupler, antenna tuner, and over here on the other side we've got going out to the antenna and reflected back from the antenna. What the antenna tuner does is it'll takes this reflected wave that's coming back from the antenna and doesn't allow it to get back to the transmitter. It rebounds it back out to the antenna again. It generates what I call a rebound wave. That's really what it does. So as far as the transmitter is concerned, it's got a perfect 1-to-1 match. And if it's a solid state transmitter, it'll put out then its full rated power, 100 watts, let's say. Most solid-state transmitters, though, if it's got reflected power coming back into it, above a 2-to-1 SWR, it'll start cutting back on its power to protect itself. So here's how an antenna tuner is put in line. Here's your transceiver. Output coax goes to the antenna tuner, and then out to the antenna. And an antenna tuner acts also, this is Dave's analogy that he uses, I think in the extra class, as a gearbox. It's a way to change the ratios of gearing here so that everything meshes perfectly. Now, here's a trick question. After matching, excuse me, if the SWR on the transmission line between the tuner and the antenna was 5:1 when you started, after you adjust the antenna tuner, what is the SWR on the antenna line? And the answer is still 5:1. It doesn't impact that at all. Rather, it just makes the transmitter happy. So keep that in mind. And we can look at impedance ratios and standing wave ratios. So if we had a 50 ohm to 50 ohm, that's a 1:1 SWR. That's right here in the middle. 50 to 50, that's a 1:1 SWR. 50 to 100 ohms, the load impedance is twice that of the coax, for example. That's a 2:1 SWR. 50 ohms to 200 ohms, that's a 4:1 standing wave ratio. Conversely, if the impedance is lower than 50 ohms, 50 ohms to 25 ohms, that's also a 2:1 ratio, 2:1 SWR. 50 ohms to 10 ohms, there's 5:1. That's a 5:1 SWR. So if you've got that reflected power coming back from the antenna, what happens? Well, it is used up eventually in the coax, and it is used up as heat, especially if the coax is lossy cable. So not this hot, but just keep that in mind. That's a memory trick there, that you're going to get heating in the coax. With a lossy transmission line and high SWR, look what happens. You're going to be losing power in every rebound. You're going to be losing it as heat in the coax. And most of the transmitted power is never radiated from the antenna. Well, let's check that out. So we've got a transmission line with a 3 dB loss. And we've got an antenna SWR ratio here at 6:1, which means it's a 50% reflection. So if we start out with 100 watts, 3 dB loss is half power. So we're only going to end up with 50 watts here. And so 50 watts, but remember we've got 50% reflection. So of that 50, 25 is going back, and 25 will be radiated by the antenna. That 25 comes back, 3 dB loss, so it sees 12.5 watts here, which the tuner is going to rebound back. But when it rebounds it back, it only gets to be about 6 watts here. 3 watts are radiated, 3 watts are rebounded back again. So 1.5 returns after the 3 dB loss. This goes on ad infinitum, infinite. But with what we're looking at here, if you add up 25 plus 3 plus 0.75, it's telling me that only 28.75 watts is being radiated by the antenna in this situation. Even though the transmitter's happy, because the antenna, what happened here? I fat fingered it. You don't see it, but I see it. I lost my, okay, hang on. There we go. So, where'd my calculations go? Anyway, there we go. Okay. 71 watts is being lost to heating in the coax. So even though the transmitter, using the antenna tuner, we've made the transmitter happy, it's putting out its full 100 watts, this is not a good situation. So you want to have coaxial cable that has low loss, and you want to get as good as possible a match with the antenna. With those two things, then more power is going to be radiated. And another thing is that with line loss in this situation, long lossy coax lines make SWR in the ham shack read better than it really is, read lower than it really is. If we look at our example again, 100 watts, 3 dB loss, 6:1, with a 50% reflection, only 14 watts is being returned, which is an equivalent of a SWR of 2.2 to 1. So our meter is going to say SWR is 2.2, where in fact it's still 6 to 1 out here. So you can't always trust the meter, especially if you have lossy coax. And the power loss at various SWR readings, here's a table that can show you that. And so high SWR and line loss, well, it's causing high total power loss in the lossy cable. Well, can I get perfect cable that doesn't have any loss? Well, probably the best cable you can get with the lowest loss is actually ladder line. 450 ohm line here. 300 ohm twin lead also has very low loss. But not many hams use this because it requires special handling. You've got to keep it away from metal objects and things like that. Ladder line has an impedance of 450 ohms, so you got to transform up to 450 ohms and maybe transform back down again. But if you've got a really long line, this might be something you'd want to do. And with open wire feed line, the characteristic impedance is based on the distance between the conductor centers, the conductor radius. All of these things, in this long formula here, will impact the characteristic impedance. Most hams are going to be using coaxial cable because it's really highly convenient to use. The small stuff, the RG58, not so much, not so popular anymore. RG8X, very popular coaxial cable, and RG8 or RG213, the larger diameter, higher power carrying cable. These are all 50 ohm coaxial cables, but you can get 50 and 75 ohm. One characteristic though, no matter what kind of cable that you use, coax is rated in decibels of attenuation per 100 feet, and loss will increase with frequency. So here's a table of various different kinds of coax. Here's LMR 400, one of the best. Here's the frequency of operation, and here's the loss in dB per 100 feet. And you can see down here for LMR 400, for 2 meters, it's 1.4 dB, whereas for RG58, it's 5.5 dB. So keep that in mind when you're choosing your coaxial cable. All right, more questions. What is the purpose of an antenna tuner?
Delta.
Not delta.
Charlie,
Then it's alpha.
Not alpha.
Charlie,
It is Charlie, yes. It increases the power transfer from the transmitter to the feed line by making the transmitter happy. It doesn't impact the SWR on the feed line to the antenna. Remember, we said it stays the same there. It doesn't reduce the power dissipation in the feed line to the antenna because that's set by the coax. So it can't be all of them, so this is the one. We say it makes the transmitter happy. And which of the following factors determine the characteristic impedance of a parallel conductor feed line?
Charlie.
Not Charlie. I'm tired. I'll give you this
Alpha.
one. It is alpha. It's the distance between the centers of the conductors, how far apart they are, and the radius of the conductors. That sets the impedance. And what is the relationship between high standing wave ratio and transmission line loss?
Charlie.
Not
Bravo.
Bravo.
It is Bravo. Remember
The
the
1-to-1 ratio.
yeah, well, a high SWR, if you have a high SWR at the antenna end and you got a lossy transmission line, that's the worst case scenario because it's going to increase loss because you're just losing power on every rebound. So what is the nominal characteristic impedance of window line transmission line? Also known as ladder line, delta, yes. No, delta, 450 ohms.
The ladder line. Okay.
And what causes reflected power at an antenna's feed point?
would be Charlie.
That is, in fact, Charlie. It's the difference between the feed line impedance and the antenna feed point impedance. And how does the attenuation of coaxial cable change with increasing frequency?
Bravo.
Bravo. Attenuation will also increase. And in what units is RF feed line loss usually expressed?
Delta.
Decibels per 100
Oh.
feet.
Yeah.
And what must be done to prevent standing waves on a feed line connected to an antenna?
Delta?
Yeah, you have to adjust the antenna feed point impedance, maybe with a gamma match or a hairpin or something, so you can match to the characteristic impedance of the feed line. Or droop those radials or other techniques. If the SWR on an antenna feed line is 5:1, and a matching network at the transmitter end of the feed line is adjusted to present a 1:1 SWR to the transmitter, what is the resulting SWR on the feed line?
Bravo.
Bravo?
Still the same, 5:1. It hasn't changed that at all. And what standing wave ratio results from connecting a 50 ohm feed line to a 200 ohm resistive load?
Alpha.
Alpha?
The ratio is 4:1, and remember the big number is always the first number, so you can't have a 1:4 ratio. SWR, I mean. So SWR is always 4:1. And what standing wave ratio results from connecting a 50 ohm feed line to a 10 ohm resistive load?
Delta.
Delta. That's
Delta.
5:1. 5:1. And yeah, slow down, read it carefully. What is the effect of transmission line loss on SWR measured at the input to the line? If you got a lossy transmission line, it's going to make your SWR go
High.
down as being measured. It's gonna look better than it really is. Higher loss reduces SWR measured at the input to the line. So that's why it can make you happier than you should be, because you're losing power in the transmission line. And that, ladies and gentlemen, is the end of Chapter 7. I did want to make sure that you were aware that this weekend is the CQ Worldwide WPX contest. It's a contest open to all hams. You could operate on the 10-meter band with your technician license, if you've got your general, on all bands in the general allocations. And you can work stateside stations, you can work DX stations, and points are calculated based on the band you're operating on and the countries, and it's just a lot of fun. It's going to be very, very busy on the bands this weekend. Starts at 8 p.m. Eastern Time on Friday. And it's a 48-hour contest, but single operators can only operate 36 of the 48 hours. And that is the end of my presentation. And we can go ahead and remove the spotlight, Dave, if you would. And do we have any comments, questions, class chat?
Quick question. Some
Sure.
of these things, I'm not sure I understand how they actually work on the traps that you put on the dipole. Do you
Yeah.
manually adjust those for different?
No, they come preset from the manufacturer. Let's go over to the blackboard if we can, Bruce. I can't get the top off. There we go. All right. So here's our feed line, our driven element, half wavelength. And so this length from here to here is resonant on 10 meters, highest frequency. And here we have a trap, and here we have a trap that anything above a certain frequency, above, let's say, 22 megahertz or 23 megahertz, is going to be blocked. but it allows frequencies lower than 23 megahertz to go to the next trap. And so then this distance is resonant on 15 meters. And then the end element, another bandpass filter here below a certain frequency. So 20 meters can use the entire length of the antenna. So that's how a trap works. They're filter elements. They're designed at the factory, and you just put them up and away they go. Now there's a coil element in there, and there's capacitance caused by the outer part, and there can be bad connections. Insects can get in there. If you put too much power to them, they can arc over, so they can fail. But generally, they're they're put up there and just left alone.
Is the trade-off on that like bandwidth as well?
They're generally pretty broad. They're generally broad enough for the entire band.
Okay.
Yeah, you can actually make traps. The ARRL antenna book, for example, has got specs in there on what size coils to wind. You can do these yourself. It's a lot simpler to just get commercially made ones, though.
So Dave, what's coming up next week?
Well, next week we're going to have another very practical chapter. Antennas is perhaps the most practical lesson in this entire series because you're all going to use antennas. Propagation tells us how we get from hither to yon, as they say. So how do you get from here to Europe? Assuming that you want to get a DXCC award, 100 confirmed countries, you'll want to know what times of the day and what frequency bands to use to get yourself over to Europe or to Australia or to California. And we're going to talk about how those radio signals get from point A to point B next week. That's propagation. And if we have time at the end, I might show you, actually demonstrate one of the propagation tools. So that's next week. So read all of chapter, what would that be? Chapter 8. Chapter 8. We're going to go through the whole chapter next week. And I'll be sending an email.
Alrighty, handouts and everything will be up at the Dropbox link tomorrow. That's linked also in the description box on YouTube. Until next week, 73, y'all.
Yep. See ya.
73.
Thank you.
73.
Thank you very much.
Thank you.
Thank you.